Ever stop and wonder how a massive database can search through a billion items and give you an answer almost instantly? It seriously feels like magic, but it's not. It's just a really, really clever way of organizing data. Today, we're going to pull back the curtain on the concept that makes it all possible: tree data structures.
So let's start with that massive question. How on earth does a computer find what you're looking for in a sea of a billion records in just a split second? The answer, and this is the cool part, has less to do with raw computing power and everything to do with smart, elegant organization. So here's our game plan for this explainer. We're going to start with the problem, what I call the tyranny of the list. Then we'll introduce a much smarter solution, the tree. We'll get into the magic of having, talk about what happens when these trees get, well, a little wobbly, and finally, we'll see where they're hiding out in the wild, in the tech you use every single day. All right, let's dive in. First, we have to understand the most basic, most intuitive way to store data, just a simple list. It makes sense, but man, when it comes to searching, it has a huge, huge flaw. Just picture a warehouse, right? And in it, there's a million boxes all lined up in one single crazy long row. If you need to find one specific box, what's your strategy? Well, you don't really have one. You just got to start at box number one and check every single one. And if you're having a bad day, your item is in the very last box. You just had to do a million checks to find it. Ouch.
Now, this whole one-by-one slog has a fancy name in computer science: O of n, or big O of n. All it really means is that the time it takes to do something grows in a straight line with the number of items you have. We just call that number n. So if you have n boxes, it could take you up to n checks. Double the boxes, you potentially double the work. Simple, sure, but incredibly inefficient when things get big. So clearly, that straight line approach isn't gonna cut it. We need a better way. What if, instead of a line, we organized our data completely differently? Let's talk about a much smarter structure: the tree. Okay, first, a quick bit of lingo. The basic building block of a tree is something called a node. You can just think of it as one of our boxes. It holds a piece of data, but here's the key difference. It can have connections, like branches, that lead to other nodes below it. Now this is where the genius comes in. A special kind of tree, a binary search tree, gets all its power from one simple, brilliant rule. Every node looks at a new piece of data and asks, is it smaller or larger than me? If the new value is smaller, it goes to the left. If it's larger, it goes to the right. That's it. This one consistent rule is the secret sauce to its incredible speed. And here's what that looks like in action. See how everything is perfectly organized? Let's say we're looking for the number 6. We start at the top, at the root, which is 8. Is 6 smaller or larger than 8? It's smaller, so we go left to 4. Now, is 6 smaller or larger than 4? It's larger, so we go right. And boom, there it is, in just 2 steps. This self-organizing system is what makes searching so fast. So how does that simple left for smaller, right for larger rule make things so much faster? Well, it all comes down to the incredible power of cutting your problem in half over and over again. Let's go back to our million boxes. With a tree, that first check we do at the root node, it doesn't just check one box. By deciding to go left or right, we instantly eliminate half of all the other boxes. Just like that, 500,000 possibilities are gone. Our very next guess does the same thing, cutting the remaining pool in half again. If you keep doing this, you can find one specific item out of a million in, get this, about 20 steps. It's amazing. And that mind-blowing efficiency has a name too. It's called O log n. While a list gets proportionally slower the bigger it gets, a tree's search time barely even budges. You could double the data from 1 million to 2 million items, and it only adds one single extra step to your search. That is a game-changing performance boost. So the thing to really let sink in is that every single decision you make, every time you go left or right, you're not just moving one step closer. You're wiping out a massive chunk of the data you don't need to look at. You're throwing away thousands, sometimes millions of possibilities with every single guess. Okay, so this O log n thing sounds almost too good to be true, right? Well, there's a catch. This incredible speed only works if the tree is balanced, meaning it's nice and bushy and symmetrical. If it's not, it can lose its superpower completely. So what would happen if you added numbers to our tree, but they were already in perfect order, like 1, then 2, then 3, then 4? Well, 2 is bigger than 1, so it goes right. 3 is bigger than 2, so it goes right again. 4 is bigger than 3, it goes right again.
Pretty soon, you don't have a bushy tree at all. You just have a long, pathetic, spindly chain of nodes all going in one direction. And in that scenario, our beautiful, efficient tree structure has basically degraded back into a simple list. A balanced tree gives you that lightning-fast O of log n performance. But an unbalanced tree? It sends you right back to that slow, painful O of n search we tried so hard to get away from. This is actually such a big deal that programmers invented special self-balancing trees that automatically shuffle themselves around to stay efficient. And just look at the difference here. It's not just a little bit worse, it's staggeringly different. For 1,000,000 items, a balanced tree takes about 20 steps. An unbalanced one? It could take up to 1,000,000 steps. That's the difference between instant and go make a cup of coffee, or maybe lunch. So here's a little cheat sheet to really nail this down. You can see that for all the main operations, searching, adding, removing, a balanced tree gives you that beautiful O log n performance on average. But in the worst case scenario, when that tree gets all lopsided, the performance for everything craters all the way back down to ON.
Okay, so I know this might feel a little bit like abstract computer science theory, but trust me, these tree data structures are absolutely everywhere. They are the unsung heroes powering a ton of the technology we rely on. Let's look at a few examples. Remember that database searching 1,000,000,000 records? Yep, its index is a highly specialized self-balancing tree. The file system on your computer, the way you click through folders inside of folders, that's a tree structure. That autocomplete feature in your search bar that seems to read your mind, you guessed it, often powered by a tree. They are truly one of the fundamental building blocks of our digital world. Okay, one final but really crucial clarification. Trees are amazing for finding, adding, or removing one specific thing really fast. But what if your goal is to visit every single node in the tree? Like say you wanted to print out all the values. Well, you still have to touch each one, right? So that kind of operation will always be O of n, because there's just no shortcut to visiting n items without doing n work. All right, so let's boil it all down. What are the big takeaways here? First, how you structure your data dictates its speed. A balanced tree isn't just a little faster than a list, it's exponentially faster. Second, that incredible O log n speed comes from one simple concept, the power of chopping your problem in half, over and over. And finally, even the most powerful tools have a weakness. For a tree, its worst case is turning back into a slow ON list when it gets unbalanced.
And that kind of leaves us with a final thought to chew on. Our entire digital world, from social media to banking, is built on these incredibly efficient structures to handle just absurd amounts of data. So what are the real-world consequences for our apps, for our networks, for our critical systems, when, for whatever reason, these fundamental trees start to fall over?